Okay, so again, applying the Euler identity, we get these with this omega. And that's very straightforward, I believe. If gamma happens to be 0, I leave it to you to verify, but the algebra is just, very simple, early algebra 2, or algebra 1 if the course is taught right, okay? Never is. But it can't be with the way we're doing things. But okay, you get this over this, and it simplifies to square root of k over m. And that's familiar from simple harmonic motion. Why should it be? Well, because if gamma is 0, that's exactly what we have. If gamma is 0, we just have simple harmonic motion. We just have a mass m with a restoring force negative kx and no drag force. Okay? Now, what we do have is something very much like simple harmonic motion, but with this decreasing exponential out here, right? Okay? So we have a decreasing exponential, so it's like we got a simple harmonic motion that would have a graph that looks like this, decreasing amplitude. This gives us essentially a decreasing amplitude. And also our omega is somewhat affected. Okay? The bigger gamma is, the smaller omega is, right? And smaller omega, well, omega is your angular frequency. So smaller angular frequency means you have a slower oscillation. So compared to simple harmonic motion, the oscillations you get here decrease exponentially in amplitude, okay? And they're slower than they would be if you didn't have the drag. Drag decreases the frequency of your simple harmonic motion. Okay, the oscillation frequency decreases. The oscillation appears to slow down. Okay? Of course, you have a slowing of a different type because of the decreasing factor out here. Also, we understand that combining these two, in general, gives you an e to the negative gamma over 2mt, okay, times the cosine of omega t plus a phi, plus a phase angle. And we understand that by the way the constants work, and we've worked that out previously. Okay? And you have a real and an imaginary part, either of which is a solution to the equation, just as is always the case when you have a second-order equation that leads you to a complex solution. Okay? So that's how we interpret this, though, in terms of an oscillator.